Today we are talking about logistic functions, and I love logistic functions because their graphs are so interesting. But before we even get into the graphs, let's take a look at what our goals are for this week. So our first outcome is to recognize the graph, and the graph is very distinctive, so I feel like that's one that you're going to obviously see the pattern, know what you're looking for, and you're going to complete that goal by looking for a real-life example of logistic. The second goal is to be able to find a regression equation, and we're going to do that with the help of our calculator. The third goal will take some work, and that is to write a logistic function for a word problem. We will not be memorizing the formula this week, but we'll be using the formula. The fourth goal is to find the ordered pair for the point of inflection. That point of inflection we abbreviated as POI, and we had that very early on in the course, so we will review that. Fifth goal is to find the limiting value. Again, we did that early in the course, so we will review that. And our final outcome is to solve problems using the graphing calculator. And we have been using the graph to solve. So again, that is review, but we will work with these in particular. So we're dealing with our first outcome of the graph. We're going to take a look at the graph. Excuse me. So the image that you see here is the iconic shape of the graph. Every logistic function looks approximately like this. Some are a little taller, a little wider, a little steeper, a little flatter, but they always have this shape. So first thing that I'd like you to do is to describe the first half of the graph. And so I'm hoping that in your head you were thinking words such as concave up, or you were thinking that it is increasing, and that you would describe it as increasing. That means going uphill at an increasing rate because it's getting steeper towards the center of the graph. Next question we're asked is, where is the point of inflection? So in way of review, the point of the inflection is where the concavity changes. So in this graph, it appears that the concavity changes approximately here. So this first half of the graph we described as concave up. The second half of the graph we did not describe, but we can see that it is concave down. And so the point of inflection is where that concavity changes. So we had labeled that early in the semester as POI, point of inflection, and that's what we have there. As far as ordered pair, I would approximate that ordered pair as 0.5. 0 right here in the middle, the 0.5 just coming over, and it looks like I'm about even between the 0.4 and the 0.6. Third, what is happening at the point of inflection? This is really important, and you're going to be asked quite a number of questions about it. The point of inflection is the steepest slope Slope describes the rate of change, so it is the fastest growth. And again, we talked about that early in the class, but now it becomes important again. In the first half, where the graph is concave up, it is increasing at an increasing rate. And the way that we get from concave up to concave down is that the rate starts to slow. And so this point of inflection is truly the fastest growth rate, and from there on, the rate of change slows down. So that comes into play in lots of the questions and applications, like this curve will describe the spread of a virus. So when is the virus spreading the fastest? It's at that point of inflection. So these superlatives here, the steepest, the fastest, all of that is at the point of inflection. Last question we have is, what is the limiting value? We have, again, talked about this previously. The limiting value is that idea of a glass ceiling or lid. And because we have that concave down shape at the end, we see the graph flattening. And so if I look here, the top of the box that this graph is in does appear to be the lid. So the glass ceiling, or the limiting value of this example, is 1. Now, we talked about finding this on our table. And we talked about when we look in our table, we're looking for when it becomes constant. And it only becomes constant because our table does round. If there was no rounding, it would increase ever so slightly. And so this one would be like 0.99999, and then the next one, there's more nines, and it's really just coming up to being a constant 1 in this example. So when you're doing your logistic in the real world assignment, you are going to be looking for this iconic shape, and you're going to be looking for this shape in everything that you graph. And so many questions will ask you about the point of inflection and the limiting value, because those are two key features of the logistic